Let's now revisit the idea of the time dependence of the wave function. So in the postulate 5 video, we showed that the wave function's time dependence, so if you have a wave function which depends on both x position and time t, that equals some spatial wave function, psi of x, and then times this time part which is tacked on at the end, which is e to the minus I squared root of minus 1, et over h bar, the reduced Planck's constant. So you get this complex exponential part, which is some oscillation tacked on at the end there. So let's look at the implications of this for the density if we just have a wave function here which is just a single eigenfunction. So that would be psi star of xt, psi of xt, the absolute magnitude squared of the wave function. And in general, again, I'm trying to write the bars over this whenever it's a wave function of time as well. That's a capital psi as opposed to the lowercase psi, which is just the spatial part. Okay, so we've got, substituting that in, psi star of x from there. And now this is where taking the complex conjugate becomes an important thing to do, because here we're going to have now plus iet over h bar, because in complex conjugation you change all of your minus i's to plus i's, all of your plus i's to minus i's, and psi of x e to the minus iet over h bar. So we've substituted in psi star and psi. So moving on to the next line, same thing, this equals. We've got psi star of x, psi of x. So that's just our standard spatial probability distribution function, the likelihood that a particle is located somewhere between x and x plus delta x, some small region there. Then our time parts here, we've got e to the iet over h bar minus iet over h bar when you multiply those exponentials together. And we can quickly see from this that this is the same as this, so something minus itself gives us 0, and then e to the 0 is going to give us 1. So we see that we get a density that does not change over time. We have psi star of xt, psi xt equals just psi star of x, psi of x. So this is true if the wave function is in a single eigenstate of the Hamiltonian. It's a single eigenfunction of the Hamiltonian. And thus these single eigenfunctions are called stationary states. Called stationary because they do not move in time. If the probability distribution function is exactly the same at time 0 as it is at any point in the future, then the particle density is completely stationary. So this is called a stationary state. But in general, we can have a wave function which is not a single eigenfunction, but is a linear combination of an infinite number of them with some characteristic coefficient for each of them. So it's a sum from n equals 1 to infinity of Cn psi n of x. Okay, so that's the general case. So what does it look like when we include the time part as well for this? Well, for the time part, we just take this complex exponential for each individual wave function and we tack it on at the end as well. So it's just going to be e to the minus I e n t over h bar. So the crucial part here is that in general this is a linear combination, a sum of these individual eigenfunctions, but each of them gets their own complex exponential. So this En is the energy of that nth eigenfunction. So in the particle in a box, if this is psi 1, this energy would be the lowest energy, would be the energy of n equals 1. It's h squared over 8ml squared. Then similarly, if this is 2, that's 4 h squared over 8ml squared, etc. So as you get to higher and higher energies, this complex exponential is going to oscillate faster and faster. So then if we very quickly look at this for the implications for the change in the density over time of a general state, what we were looking at up here was just being in one eigenstate, one eigenfunction. Then that's going to be, I'm going to go ahead and go to the next line because this is going to be quite long to write. We have the sum from n equals 1 to infinity of Cn psi n of x e to the minus I e n t over h bar, all of that times sum of m equals 1 to infinity. Because this is going to be a completely independent index, this is another psi, so this index over here, n, is independent of this index m, so we need to give it a different name, thus we're calling it m. Cm psi m, and again, making sure we do a star here, making sure we do plus here, because we're taking the complex conjugate. I almost forgot about that. And then e to the minus I e m t over h bar. Okay, so that's that one, and then we can make, I believe, one more nice little simplification out of that, is we can write this as a double sum. So there's an inner loop and an outer loop here of n equals 1 to infinity and m equals 1 to infinity, where we're going to have Cn star Cm psi n star of x psi m of x. Then we have e to the minus I em, do a better em minus en t over h bar. So you see, for this minus I, we have minus I em, so that's the minus I em part, and then we have a plus I en, so a minus I minus en gives us the plus en. So these two complex exponentials we factored together to get us this time part, which is the e to the minus I em minus en t over h bar. So the result of this part here on the end, this part here at the beginning is just the standard density. It's the standard spatial density. This would be the same if we weren't looking at it with respect to time. But this part at the end here is going to give us some oscillation in the density over time. So that oscillation over time is going to mean that things like the expectation value of position will change over time. And for a particle in a box, we saw that for an individual eigenstate, the expectation value of momentum was 0. But since the expectation value of position, if we have a wave function which exists partly within multiple eigenfunctions, we're going to have an expectation value for position which varies in time. And if position varies in time, then momentum is going to be non-zero. So if we calculate things like the expectation value of position for this, we're going to see it changes in time, and momentum is going to be non-zero. And in the next video, we're going to take a look at that in MATLAB and look at some animations of what a particle in a box wave function looks like over time.